Okay, it's recorded. Okay, so inverse. So before we learn about inverse in detail, the first thing to know that the inverse is that it has to be one-to-one function, so that it has an inverse. Okay? So one-to-one functions and then inverse. So what is one-to-one function? To get more illustrated visuals, there's two conditions here. Okay? The first condition, each element or each point in each element, they have certain amount of value. Whether at the second element or the second picture, from A, there are two elements that is have the same amount of value or amount of element. Okay? Which means I draw a graph like this. It's a sine graph, sine x. Let's say we have a sine x. Okay, let me zoom in. If I'm asking, is this one-to-one function, the whole sine x? No. Okay? Okay, agree? No. Because at some point here, let's say this is A, and maybe this is B. At x equal A and x equal B, they have the same value. They have the same f of x, which means that it is not a one-to-one function. Okay? And we can illustrate how it looks like with a certain line like this one, the horizontal line, and we call this horizontal line test. When we have this line and it is crossing the graph more than one, which means it has two now, then it is not one-to-one function. So the whole thing here, the sine x, in all interval, from especially if you look on A and B, it doesn't have any inverse. But we know that we learn about sine inverse, right? We learn about sine inverse. That is because the sine inverse, the case sine inverse, let me write sine inverse. We know that we have sine inverse. That is because we restricted the domain. We restrict the domain. If you look from this point here, and maybe here, if we are using the same techniques, the horizontal line, it's exactly one, right? Exactly one. And that's one-to-one function. And that's why on this domain from here to here, or let's say in case of this sine, this will be negative pi over 2, and this is pi over 2. From negative pi over 2 to pi over 2, those intervals, we have one-to-one function, or we have exactly, when we are using the horizontal line, it's exactly crossing 1, 1, 1, 1, 1, right? Okay, one time crossing. Okay, and that's why we call and we can draw the sine inverse from this sine. Okay. Okay, let me write in the new page the official definition. So one-to-one function I hope my writing can be read. It never takes. And you can check with the horizontal line test. To check. To check whether the line cross or intersect the graph. More than one. So that is the one-to-one function. Now from these definitions, we can move to the inverse. Okay, the inverse. After one-to-one functions, inverse, and we can move on to at least moving to the calculus part. Okay. Because chapter 1 is actually the fundamentals of functions and all the terms inside before we jump into the calculus. Okay, so inverse, we set up by assuming or make a statement that let a function be one-to-one functions. That's the first assumption or statement that we need to take on. And let's say we have a certain domain, let's say domain A, and a range B. Maybe let me make it into different color. Then its inverse function has domain A or domain B, sorry, and range A. And it's defined by okay. So the inverse, I think I also mentioned in the last class, that the inverse means that you have certain domain, you have certain range, and when you have the inverse, you are exchanging the domain and range. Okay. And if we are exchanging domain and range, which means that we are changing our y and x. And remember, although we are writing the inverse like we have -1 like this one, this superscription like this is not the same, okay? Not the same, okay? This means inverse, okay? This means inverse. Okay, just a little description. For example, okay, if you have the f of x is x cubed, okay, what is the f inverse? How to find is usually you're writing like this, and you're exchanging the x and y, and then you can know that this is right. Okay, I will later maybe repeat the method to make sure that you got my point. Okay. You can check also through the graphs. Okay. The x cubed, you have something like that, right? And when you have the x to the power of 1/3 or cubic root of x, you are just actually rotating the graphs. Okay. Just like in the x squared and square root of x. Okay. So let me write here just to give you the easy graphs. For square root of x, it should be, they have this, but since, remember the rules, so we're only having this part. If you look at, it's actually similar, kind of similar graphs, right? Kind of similar, and it's actually similar with the cubic example also. And then another note is when we have this inverse, if we are putting this y inside, which means we are going to put the x cubed, and then we are having the 1/3 from here. Okay. This will brings back these terms here, okay, which we can consider this as a property of inverse. This is true for every x in the domain A. And we can also plug in the inverse inside the functions, and we will also receive the same x. This is also true for every x in B, okay, because we are using A and B in the first terms, domain and range. Okay. But what's the deal here is whenever you have the inverse, when you put the functions, the original function inside that inverse, it should revert back to x, just x. And when you have the functions, you put the inverse inside, it's also will revert back to original x. Okay? This is a simple way, but sometimes in calculus, some method they need to look on this simple way, and then you can actually get the conclusions. Okay. For example, if you imagine this, and maybe we can have some like the derivatives part later on. Sometimes they need to be simplified. sometimes. So the idea here is actually, if you remember, or maybe I haven't mentioned that if you have x, okay, it's like you input something to your computer, right? And this is your computer. This can be anything that you can input, okay? And this is your computer. Your computer has some processor, right? It can think, right? So the function is actually programmed like a program. It's programmable, right? And it will give you some output, which is the function of x, because you input x, and so the end result should have something with x, right? And then from here, you put the inverse. You put the inverse. What you are actually doing here is you are undoing. You are taking the undo. That is, you get back your x. Okay? Okay. I think some of you are already familiar with some programming. You will understand what I mean with this process. Okay? Okay. Okay, now back to the visuals. Okay, from here. Okay. What is exactly happened here? Okay. There is actually a pattern. If you check with the other functions and you check its inverse, there will be a pattern. Okay. Maybe I will draw maybe right here. Let's say I have just a random functions, and imagine this is one-to-one function. What do you think the inverse will be? Where do you think? Here, right? Okay, yeah, got it? Okay, here. So it's actually, if you draw a line, it's actually mirroring this line. So it's like a mirror, okay? So you will have the inverse around like that. Okay, let's say this is the inverse. And this line is actually y equal x. Okay, so the graph can be obtained. So graph of inverse can be obtained by reflecting graph of f about line y equal x. I think the best way to look on what kind of graph that is, or what kind of function that is important to note for its inverse is, example is the e to the x, right, the exponential. The inverse of e is log. Okay. log or ln. In this case, it's ln. This is inverse, and you can prove that in the graph. I think it's in visuals it is easy to be proven. Your graph of E like this, and your log is right here, right? If you remember the E and then log. Maybe like that. And the log will crossing from around here. Yeah, maybe something like that. This is the log, this is the E or exponent, an exponent. Well, we will see more on the exponential later on when we are dealing with derivatives. Okay. I will also review a little bit about the exponent, how we will get the number E through the limit. So before we are moving to the next section, I just want to make sure how we can find the inverse from any functions you can find. So from here, it's actually a shortcut to how we find the inverse. Is first we are writing our functions in terms of x and y. Y is a function of x, but we are writing in y to help you calculate in algebraically. So y is equal x cubed, and we are solving in terms of x, so we got our y with the cubic root, okay? And then to make it into our definition of inverse, we are changing our x with f inverse. Okay? Actually, you can skip this second part if you are familiar enough with the inverse. You can go to here, and you will see that, okay, I need to solve this, and you will get this cubic root. Okay? But to help with, we can exchange, or we can solve x in terms of y, and then later on we are exchanging x with f inverse. Okay? And that's how you are using the, or calculate the inverse. Okay? And I hope you guys are already familiar with the exponent and the log. Okay. If we need some discussion, we can have later on when we are dealing with the derivatives part. So this is all the fundamentals. Okay. In my opinion, that is particularly important. Okay. Okay. Now we move on to chapter 2. Okay, chapter 2, the calculus one. Any question from here? No, I think still okay, right? Because this is just a basic function. Okay, so right here. So this is chapter 2. We start with the tangent and velocity problems. Okay. So tangent is, or the literal meaning of tangents is to touch, right, or touching. Which we can usually describe in every math, like you have a circle and you have a line, and it will touch exactly at one point. If you see this picture here, because of course, the pixels and maybe the thickness of the line itself, we can really see where is the point, right? Because it's simply from here until here seems touching, right? But actually, in the definition, tangent means really one point. Okay, one point, touch one point. So touching exactly one point. Okay, now if we are using the simple parabola, okay, let's say this is our usual y equal x squared. Unless we have maybe at this point, or maybe here. Let's say at 1, 1. At 1, 1, let's say we have some tangent. I think I draw too small. Let me take this a little bit higher. Okay, maybe around that. So let's say this is our tangent line on this point 1, 1. Okay. Now, before we learn on how to find the tangent using the limit, derivative, and so on, let's try with traditional way to find how we find the tangent. Okay. So first, we need to have the additional point. Let's say just a random point, maybe here, or maybe here or here, any point you like. But we are putting our point based on the equations x and x squared. Okay, let's say we have this point here, the green one. Okay. Now, if I draw a line that's connecting the red line and the green line, I can calculate the slope, right? It's slope. Okay. Let's say we have the slope for, let's say, if this is maybe Q, maybe this is P, then let's say we have the slope of PQ. The slope of PQ, we can use this triangle here, right? Use the triangle, let's say here. This is the delta y, delta x, and the slope is delta y over delta x, right? The slope, the delta y, this is x squared, okay, x squared, and this is having 1, so this will be x squared minus 1, okay? So I will write here, this will perfectly be like this, and the delta x is just x and then minus 1, right? Okay? And now, this point here, the green one, we can input any numbers, right? We can put maybe 1.5, maybe 0.5, any point, any number that we can input. Our goals, okay, our goals is, because we want to know what it looks like here, okay, at this certain point here. But of course, if we are using the exact same point, because it's 1, 1, of course we are not getting any conclusions. So it's like finding the best way to approach the point P, so that we are able to find the slope here, or the tangent. Okay. And then we can have some table values for x and the results of the slope. If we input 2, it will be 3. If we put smaller, we get this. If we put smaller, we get this. And then we can put nearby 1, 1, 1. Maybe 1, maybe this is to make it the same, so 1.01. This is 2.01, and then 1.001, 2.001. Okay. Or maybe we start from 0. We start from 0. It's getting 1, and then start half, 1.5, 0.9 it's 1.9, and 0.99 it's 1.99. Okay, so what does this table do is we are checking every point that is possible for this grid point here. It can be here, so we are approaching from right to this point, which is what we are going to do with this number 2 until nearby the 1.1 or 1.1. Or we can go from at least left side, from 0, going right, going right, going right, up until nearby 1. It's 0.999. The conclusions, what we have seen here, is getting closer to this number, right? Okay, it's getting closer. Let me write here. It seems getting closer to 2, right? Okay. Now, to help our calculations, we need another tools to make up this small number. To make up this small number, that tools is limit. Okay, that tools is limit. So we say that if this is the tangent, the line that is connecting the green and red is called the secant. Okay? I forgot to mention. This is the secant. Okay, so slope of tangent line is the limit of slope of secant line. We symbolically express the terms as limit approaching, I forgot which, Q, okay, Q to P. The slope of PQ, we can call this as its M, which is the tangent. So this is secant, this is tangent. The tangent, secant. Secant means it's actually cut. Okay, so if you have graph and you connecting line from points on the curve and it's cutting the curve, it's called the secant, like we did here. This is the secant. Let me draw. Okay, the pink one, it's the secant. Okay. So when we have the limit as x approaching 1, according to our problem, the x equal 1, right? Of our secant this should be 2, but it seems that we need more adjustment and more definitions later on. This is not input the one here. Okay, different. This is from our visuals, okay, from our definition. So we need to, let me just take some question marks, and if this is true, then in our line equations, this is line equation, by the way, if you forget to write the line equations. So at 1, 1, and at m equal 2, we will get, or we have y equal 2x minus 1. Of course, later you can check this when we learn derivative, or when we are, actually we can simplify this and factorize this one, and we get x plus 1, 2, right? But let's just, we will go back here later, okay? Okay, to note that, let me check my graph. Okay. Okay, so we have two conditions, like I said before. The point Q we approach from the right, and the second case is we are approaching from the left. Okay? Actually, it's approaching from the far left, okay, below 0. So from here, this is the secant line is changing, it's changing, and then it's getting closer to P. Okay, and this is also changing from the right, far right, going to the P, closer and closer. Okay. From this phenomenon, okay, we will develop the terms limit, which means that if you're getting closer and closer to something, and you know that there is small numbers, okay. For example, we say 0.99999 is a number, right? But in terms of limit, we can say it's 1. It's 1 in limit, okay, in terms of limit. Okay. So it helps calculations, it helps some, of course, we are dealing with calculus, right? Because calculus, we are dealing with something that has changes, okay, or we can call it rate of change. Okay. Because calculus is one section or one domain in mathematics, okay. And it's focused on only looking on something that changes, like rate of change, anything. We calculate the derivative, integral, all the things in calculus is basically rate of change, and we are usually write in terms of d something dx or d something blah blah blah, right? The rate of change. Okay. And in terms of rate of change, to help us calculate, the first tools that we getting is limit. Okay. We will see the limit when we prove the derivative, when we prove the integrations, we are going to see the limit of that. Okay. 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 So another problem to get the idea of limit, okay, we call the velocity problem. Okay. Okay, let me take this into the next page. Velocity problem. Okay, if you have a ball, it has a distance of 400 meters. The ball is going down. And we know that there is an equations of the distance that is depends on time. Okay. The questions find velocity of the ball after 5 seconds. Okay, if you don't have any terms yet for calculus, derivative, and so on, then how do we calculate this? We know only like 5 seconds, after 5 seconds. Okay. What is the velocity or average velocity? This is the change in position, right? Over how many times that elapses, right? change in position. So it's based on the functions, right? But the problem here, okay, so there's a problem actually here. But before we continue, do you want to have break or maybe no? And we can have quicker lecture.
I think we can continue.
Continue, okay? Is that okay? Okay. Okay. Okay, so there is a problem here. Okay, so there is a problem in this question, which is there is no time interval because we don't know the conditions. Let's say it's 5 seconds, but 5 seconds from what? Or probably if we are dealing with the 5 seconds, we can think this as maybe from 5 to 5.1. Okay, probably. Let's checking the numbers. Let's check the numbers. So we can take this into some calculation. And this will be resulting 0.1. And we can input our formulations. And then you can check if you want, but the result is around 4949 meter per second. Okay, that is from 5 to 5.1. So we have 0.1 interval. Okay, we have 0.1 interval. Let's take another interval. So 5 to 5.1. Okay. So let me write here, we have 5 to 5.1. And we have results that is 49.49. And let's check the shorter interval. So let's check 5.01. So we have 0.01 seconds. And it's resulting that is 49.049 meters per second. If we input into the same formula over and over, and then let's make it shorter. We get that this is 49.0049. Meter per second. And it is, again, similar to the previous problem. When we make it closer and closer, or shorter and shorter, the interval is getting shorter from 0.1, 0.01, 0.001. If you take maybe 0.00001, you will have a number that is 49.000 something. Okay? But still, okay, in terms of numbers, in mathematics, this is not equal with 49 or 49. Okay? But we can say that the velocity getting closer to 49. We can say that. But we cannot say that this is equal. Okay? It's fundamental, so it's different. So when t is getting closer to 5, then the velocity is closer to 49. Okay? Now, from this, small experiments, okay, we see that we are getting the idea of getting closer, right? Getting closer. Or, if you remember the terms, we called instantaneous velocity. Maybe in physics also using the same terms. Instantaneous velocity. This means that this is velocity that happened instantly after 5 seconds. So it's really short in short period of time. Okay, hopefully from the tangent problem and velocity problem you get the idea on how we can define our getting closer, the concept of getting closer in limit. Okay. Because sometimes when I was still your age or maybe younger than that, I'm not sure because of the educational system or maybe some teachings, sometimes we forget on how we are dealing with the subject. Like for example, when we learn math, we just learn, okay, we calculate and find the answers. Okay, we got the answer, but we don't really know why or how or what is actually going on. Okay. So basically, as a university students, you are expected to at least define and know how. Okay, to at least define and know how. And if you still confused or maybe not really good at fundamentals, then you just keep on reading, you just keep on studying. Okay. Sometimes even when you graduate, maybe you still don't understand or on some specific subject sometimes. Okay. But that's still okay. As long as you keep your curiosity, keep your intentions to study and trying to understand. Okay. And exactly in math or calculus, the point. Okay, if we draw this 1 over x squared this is at least how it looks like. It should be a little bit closer to the axis. Okay, we call this 1 over x squared. Okay. Now what will happen in x equals 0? Both way from the left and from the right, it seems that it's getting larger, larger, and larger. It's getting some infinite point of number, right? And this is where we are having another terms in limit that we have infinite limits. And how to notice that we have infinite limits? How to notice that? We will have a vertical line in the middle we call asymptote. Okay? The vertical asymptotes. And then we can write that the limit as x approaching 0 of 1 over x squared is getting infinity. And to note that this infinite means, again, I think I haven't made some statement about the infinite. Infinite is not a number. Okay? Okay, remember this concept. Infinite is not a number. It's an idea. It's an abstract. So you can't or you cannot take this as your number. Okay? This is just to show that there is some large number that you are not able to be count on. Okay? So officially, if we let the functions define on both sides of A, except possibly at A itself. It's similar with what we have before. Then so meaning, okay, it's here, the meaning means f of x can be made as large as we please. By taking x closer or sufficiently closer to A, but not equal A. We can also write the terms of limit as f of x getting closer to infinity as x closer to A. We can also write that. And another way, instead of positive infinity going really, really large, we can also have negatively large. Okay? Negatively large. So this is the first, the second limit as x approaching A. You can write as a negative infinity. Means that this is negatively large. I would like to say like smaller, but it seems that it's wrong. But it's just say negatively large. So that it's not really confusing. And the same thing with the one-side limit. Okay, it's also the same. We can say from right side and getting positive infinity or negative infinity, and from left side also the same, going to positive or negative infinity. Okay. Okay, and then another note on the vertical asymptotes. Let me take this onto the right, the left side here. Okay, I think here. Okay. let me take just some quick illustrations. This is we say x equal a. Okay, x equal a is a vertical asymptote of curve. Let's say this is y equal f of x. Y equal f of x if one of following is true. Should be put infinity. Okay. So we have a lot of limit here, but if you already have one is true, then we can have the vertical asymptote. So it's quite more intuitively faster. We can recognize whether it's asymptote or not. You can just checking from one side, and then if it's having infinite value, then you will recognize that as a vertical asymptote. Okay. Okay. Just one last note, and I think we can finish. And we will continue next Monday, and I will give you maybe some exercise, like how to read the graph and how to check whether its limit exists or not. Okay. Okay, let me take some notes here, or maybe example. If you have the curve, let's say 2x over x minus 3. Okay. I think if you look on the rational functions, okay, let's take this as a rational function. If you look on the denominator, when x equals 3, it's undefined, right? So, of course, if you happen looking on this kind of functions or curve, we will have at least at x equals 3, this will be undefined, right? And of course, if we are looking in terms of limit, we know that this will be a positive number because it's greater than 3, right? So we will have, at least this is when it's reaching or closer 3, we will have a positive infinity or just infinity like this, right? And here will be negative infinity. Okay. So if we are looking at the limit itself at x approaching 3, because it's having different different conclusions that the limit is that it actually doesn't exist, but it still has the asymptote. Okay, still has this asymptote. If you draw, probably it will be maybe here's the x equal 3, and maybe this will be the curve. Okay. So we will still have the asymptote here. But in terms of the limit itself, whether its limit at closer 3 exists or not, and it doesn't exist. Maybe I can write here that the limit itself, it doesn't exist. Because of the difference in right hand limit and left hand limit, right? Okay, I think I can stop until here. I will give you more quick review next Monday with some practical graphic to read and to have some exercise. And yeah, I think that's all for today. Okay.